Hello guys, so welcome back to our lecture 21. So in this lecture, we're gonna, discuss or study something very interesting, which is basically any amplifier characteristics, not just VGT amplifiers, but any amplifier characteristics. Okay, and this answers very important question. If you wanna compare two amplifiers together to say which is better, so how can we answer this question? Basically by determining the characteristic of each one. Then we by comparing them, the characteristics, we can say which is better. Okay. To do that, we're gonna explore very some amplifier circuit. The one that we see in front of us is of course one of example of many thousands of amplifier circuits. Okay. So let's divide this circuit into some parts. Then basically we're gonna abstract our analysis to get these characteristics all together basically. Okay, so the first part of any amplifier characteristics is any amplifier circuit is the input part, which is basically this part in here. Okay, so let's analyze the three elements we see in this part, the input part, the input part. So we have the signal, which is basically the signal input to be amplified. The small signal that we want to amplify, basically. What is our signal? For now, we're gonna call our signal the internal resistance of the signal, the source of the signal. For now, internal resistance of the source V signal. In the future, we're gonna learn is that our signal is more than this. It can be basically an output resistance of another stage that basically feeds this amplifier circuit with V signal. And V signal is not a source by itself. V signal is basically an output voltage for another amplifier circuit or another circuit, whatever it is. Not necessarily a source like a mic or a voltage source. Okay. C input is basically a coupling capacitor. This is so CO here and the C input are called coupling capacitors. Okay, and I explained this in the last recording. These coupling capacitors, so CO, as we will study in just in a moment or in a minute, isolates the DC of the circuit from the load. Okay. C input, however, do the same job, but it isolates any possible DC in this V signal, in this source, from from altering the DC Q point of the amplifier circuit itself. Okay, because V signal, although it should be an EC voltage, but again, if this V signal is coming from an output of another circuit, this circuit might have a DC bias as well. So this might alter the DC Q point of this amplifier circuit. So we must also isolate this DC that might be in the input, might be, not necessary. Okay. So this is the first part. The second part, let's do it with another color, which is basically the output part in here, which is really simple. This is the output part. You have CO, which isolates, as we discussed last time, isolates the DC of the amplifier circuit from to be fed to the load. And this is basically the load. The load that we want to feed with the amplified version of the signal, the input signal here. Finally, the most important part 3, the amplifier circuit itself. This is the amplifier circuit. Okay. So it's a transistor and some resistors and some sources like VCC for biasing. Okay. So we have 3 parts here. We have the input part, we have the output part, and we have the amplifier circuit itself. Okay, good. Now we can abstract such circuit or any amplifier circuit basically into this configuration here. An input part, an output part, and this is basically the amplifier. Input part, output, load, and the amplifier itself. And this is basically a symbol for the amplifier. This is basically a symbol for the amplifier. Okay, good. Let's go back to our normal color. You guys remember V Thevenin and R Thevenin. When you look between two terminals of any circuit, you should find or you should abstract or should, you know, there will be an equivalent for this circuit between these two terminals as a voltage source and resistor, V Thevenin and R Thevenin. Okay, that's what we're gonna do now. So if we look between the two terminals of the source is basically these are the two terminals of the input, this point and this point near the ground. If we look between these 2 points, we can abstract everything beyond these 2 points into V Thevenin and R Thevenin. What is between these 2 points? Basically all of that. All of that. Okay. But if we look here, remember now this is AC. We want some AC. So in AC, we're gonna ignore the VCC, which is, you know, a voltage source. So we're gonna ignore VCC for now, and I'm gonna prove for you in the next video that we should ignore VCC when we talk about AC stuff, the amplification stuff. So if we look here, we're gonna see a circuit with no AC sources, but only resistors. So basically V Thevenin will be 0, and you will only have R Thevenin, which we're gonna call our input. Why? Because basically we are looking between the 2 terminals of the input, V signal and R signal. So we can reduce the amplifier circuit into our input like this. Or we can say we're gonna find between these 2 points the input resistance or the input equivalent resistance of the amplification circuit, or input, this one here. Good. Now, what if I look between the 2 terminals of the output, between these 2 terminals? Basically this point and this point, which is the ground. So I can reduce all that circuit into V Thevenin and R Thevenin. But this time we have AC source. Again, ignore VCC. You know, we are talking about AC right now. And I'm gonna prove for you, I'll convince you in the next recording that we should, yes, ignore VCC. So we have now V signal, and we have some other resistors, you know, R signal and those guys, okay, for the biasing. So if we look between the 2 terminals of the output, we're gonna see R Thevenin, which we're gonna call RO, the output equivalent resistance of the amplifier circuit, because we are looking basically between the 2 terminals of the output, and a voltage source. A voltage source. So that's what I have done here in the, you know, in the with the abstract circuit. In the abstract circuit, we look once from here and once from here. Once between the 2 terminals of the input and once between the 2 terminals of the output. Okay, and based on that, we can remove this symbol of the amplifier and put this configuration here in the square. So this abstract circuit here, let's enclose it in green, is equivalent to this one. but in a more abstract way and understandable way, basically. Good. Now let's go back to our original, purpose of this recording: amplifier characteristics. Where are the amplifier characteristics? We just highlight them now. Basically, just look at this internal square, because this is the amplifier. Basically, we don't care about the input, we don't care about the output, we care about the amplifier. We want to know the amplifier characteristics. So in here, you're gonna find our input. So the first characteristic is our input. You're gonna find our output. The second characteristic is our output. And then look, EVO, VI. What is this basically? This voltage source is interesting voltage source. It's not just a normal voltage source. It shows you how we could amplify the input that goes into the amplifier circuit. Okay. So what is VO? VI here is the voltage input across the input. So we wanted to amplify V signal, but since there is V signal here, our signal here, some of it goes to our signal and some of the V signal goes to our input. And that's what we basically amplified. Unfortunately, we can't amplify 100% of the input voltage. Why? Because the input voltage, the input signal, V signal, has some internal resistance or signal that will take some of its voltage by voltage divider, of course. And the other part, which will go to our input, we're gonna call it VI. VI is the portion of V signal that will be amplified. Amplified by how much? By AV, our third AV node, basically. Okay. AV node is a sim or abstraction or abbreviation for open loop gain, open loop voltage gain. And I'm gonna explain what is open loop in a moment. Okay. Good. Let's now clean up the mess here. Just to start from a clean, drawing. So we have three characteristics: the input resistance of the amplifier, or the amplifier input resistance, the output resistance of the amplifier, and the open loop voltage gain. Let's discuss them one by one. Okay, let's go back to our normal color. Number one, the amplifier output resistance. So for each one of those characteristics, we're gonna answer one very simple question. Do we want this characteristic to be high or low? Big or small? Okay. So we're gonna ask this question first to the amplifier output resistance, RO. Do we need RO to be big or do we need RO to be small? And that's really easy to answer. Just look at the output circuit. Here is the output circuit. You have the output equivalent, which is basically EV node, VI, and you have R load. Okay. Now, remember, the main function of this amplifier is to deliver an amplified input to RL. Here is the amplified signal. This is the amplified signal. And it's a source and there are two series resistances, RO and RL. So by voltage divider, VO equal to AV node, the input, R load over R load plus RO. So not all, so some voltage will go to RO and some voltage will go to RL. It's a division. Now, to know which is better, a high or low output resistance, just look at this equation. If RO is small, VO will be bigger. I mean, more portion of AV node VI will go to VO to RO rather. I'm sorry, RL rather than RO. Or let's call it V load, not to confuse you. V load. So the less RO, the higher V load. The opposite. The more RO, the less VL. Try the two extremes. If RO equal to 0, then basically VL will be equal to AV node VI. All the amplified signal goes to the load. If RO equal to infinity, I mean open circuit. That's what I mean. You know, this is a reachable, you know, target in resistances to have infinity. Just to make it open. Okay. So what is V load in that case? Let's do it. V load equal to AV node VI, then divided by RO or divided by RL. You know, so this will be 1 plus RO over RL. So basically, this will be infinity. So AV naught VI 1 over infinity, 0. So definitely, the smaller the RO, the better. The smaller RO, the better the amplifier. Good. Number 2. The amplifier input resistance is this time. Ri. Do we want Ri to be big, high, or low, or small? Okay. Again, draw the input side now. I'm gonna draw V signal and R signal. And Ri. We said that in the beginning, look, the amplified version here, the amplified output voltage is not EV naught V signal, the original signal that we wanted to amplify, no. But it's EV naught VI. And what is VI? Is basically the input across the input, our input. Why is that? Because of this damn R signal here. Okay, because just look at this circuit, very simple circuit, 2 series resistances. So V signal will be divided between both. Some will go to our signal, some will go to our input. The portion that go to our input is called V input. And it's definitely not 100% equal to V signal. No, it's a portion of it. 80%, 70%, whatever. Might be 50% or even lower. Okay. So VI here, which we desire to be exactly equal to V signal, equal to V signal by voltage divider, R input over R input plus R signal. Now we're gonna ask ourselves the same question. Do we want our input to be high or low, small or big? Just to try the two extremes. So both R input equal to 0. If we put our input equal to 0, the input, just to substitute here, the input will be 0. That's really bad. That's really bad. If the input is equal to 0, then AV, the input here is 0. So the output or V load will be 0. No amplification. Bad. Okay. Because there is no amplification basically. That's basically attenuation, not just that's attenuation. We just killed the output. How about if our input equal to infinity? Let's do it. V input equal to V signal. Just divide by our input. So 1 over 1 plus R signal over R input. V signal. If our signal over, if our input is equal to infinity, our signal over our input will be 0. 1 over 1 plus 0, this is equal to V signal. So in that case, all the input goes to our input. So here, this will be EV, not V signal. So all the signal is amplified. So that's the perfect, the perfect situation. So the higher, the better. The higher, the better for the amplifier or for the amplification in general. Okay, number 3, AV naught, the voltage gain, open loop voltage gain. AV naught. AV naught, open loop means the amplification measured or calculated or estimated when there is no load, when the load is infinity. So this is basically not any gain. This is the gain calculated when the load is not there, infinity, open circuit. Just to know the definition of it. And it's really important. That's intrinsic, characteristic because there are many amplification, as we will see in the next lecture. There are many types of amplification. This is the intrinsic one. Others are not intrinsic. I mean, by intrinsic, it depends only on the amplification circuit, part 2. This part, the green part here, doesn't depend on our signal or V signal, or doesn't depend on our load. That's what I meant by intrinsic. And that's really easy to answer here. Do we want AV naught to be big or small? Of course, we want it to be big. So the higher, of course, the higher, the better. For sure. Okay, that's basically the function of the amplifier circuit, is to have amplification. Okay. So now if we have 2 amplifiers and we want to compare between them, we're going to look at these 3 basics. There are, of course, other, characteristics, but these are the most important 3 characteristics or parameters. Okay. The gain, the input resistance, and the output resistance. These are the basically, the basic 3. Just look, for example, if 2 amplifiers have same gain and same output resistance, but one of them has more input resistance, then this guy is better. If 2 amplifiers has same gain, same open loop gain, same input resistance, but one of them is lower in output resistance, this guy is better, and so on. Okay, guys, that was basically the first exposure basically to amplifier circuits. Okay. The next recording would be the last recording in lecture 21, in which we're gonna give you the highlight how to solve or how to analyze amplifier circuits. Then starting from the next lecture, lecture 22, we're gonna deep now in the amplifier circuits and analysis of amplifier circuits. Okay, guys, thank you very much for watching this video, and see you in the next video. Bye-bye.